Introduction. Solid-state chemistry is also known as solid bonding. A chemical bond is a net attractive force which holds two particles, atoms, molecules, ions together to form a new solid. These particles bond by electrostatic attraction forces between each other to become more stable. Think about it. If you're not solid, you will be nothing, not even water or cloud. Thanks to solid bonding. Objectives. At the end of this lesson, you'll be able to describe general characteristics of solid state, distinguish between amorphous and crystalline solids, classify crystalline solids on the basis of the nature of binding forces, define crystal lattice and unit cell. Classification of solids. Solids can be classified as crystalline or amorphous on the basis of the nature of order present in the arrangement of their constituent particles. Crystalline solids are anisotropic in nature. Anisotropy in nature is due to different nature of particles along different directions. Amorphous solids. Amorphous solids are also called as pseudosolids or supercooled liquids due to their very slow tendency to flow. Examples. 1. Glass panes fixed to windows or doors of old buildings are invariably found to be slightly thicker at the bottom than at the top because of the glass flows down very slowly and make the bottom portion slightly thicker. 2. Amorphous silicon is one of the best photovoltaic materials available for conversion of sunlight into electricity. Difference between crystalline and amorphous solids. Classification of crystalline solids. Crystalline solids can be classified on the basis of nature of intermolecular forces operating in them into four categories like molecular, ionic, metallic, and covalent solids. Classification of molecular solids. Molecules are the constituent particles of molecular solids. These are further subdivided into the following categories. Nonpolar molecular solids. These solids are soft and non-conductors of electricity. They have low melting points and are usually in liquid or gaseous state at room temperature and pressure. The atoms or molecules are held by weak dispersion forces or London forces. Example, H2, Cl2, and I2. Polar molecular solids. The molecules of substances are formed by polar covalent bonds. The molecules are held together by stronger dipole-dipole interactions. These solids are soft and non-conductors of electricity. Their melting points are higher than those of nonpolar molecular solids. Examples: HCl, SO2. Hydrogen-bonded molecular solids. The molecules contain polar covalent bonds between H and F, O or N atoms. They are non-conductors of electricity. They are volatile liquids or soft solids under room temperature and pressure. Example, H2O, ice. Ionic solids. Ions are the constituent particles of ionic solids. They are formed by the three-dimensional arrangements of cations and anions bound by strong Coulombic electrostatic forces. These are hard and brittle in nature. They have high melting and boiling points. They are electrical insulators in the solid state. They conduct electricity in molten state or when dissolved in water. Metallic solids. Metals are orderly collection of positive ions surrounded by and held together by a sea of free electrons. These electrons are mobile and are evenly spread out throughout the crystal. These free and mobile electrons are responsible for high electrical and thermal conductivity of metals. Covalent or network solids. Covalent bonds are strong and directional in nature, therefore atoms are held very strongly at their positions. Such solids are very hard and brittle. They have extremely high melting points and may even decompose before melting. They are insulators and do not conduct electricity. Examples: diamond, silicon carbide. In graphite, carbon atoms are arranged in different layers, and each atom is covalently bonded to 3 of its neighboring atoms in the same layer, which can slide one over the other. This makes graphite a soft solid and a good solid lubricant. Crystal lattices and unit cells. A regular 3-dimensional arrangement of points in space is called a crystal lattice. Unit cell is the smallest portion of a crystal lattice, which, when repeated in different directions, generates the entire lattice. A unit cell is characterized by 1. Its dimensions along the 3 edges A, B, and C. These edges may or may not be mutually perpendicular. 2. Angles between the edges: alpha between B and C, beta between A and C, and gamma between A and B. Thus, a unit cell is characterized by 6 parameters: A, B, C, alpha, beta, and gamma. Primitive and centered unit cells. Unit cells can be broadly divided into 2 categories: primitive and centered unit cells. A. Primitive unit cells. When constituent particles are present only on the corner positions of a unit cell, it is called as primitive unit cells. B. Centered unit cells. When a unit cell contains 1 or more constituent particles present at positions other than corners in addition to those at corners, it is called a centered unit cell. Centered unit cells are of 3 types. 1. Body-centered unit cells. Such a unit cell contains 1 constituent particle, atom, molecule, or ion at its body center besides the ones that are at its corners. 2. Face-centered unit cells. Such a unit cell contains 1 constituent particle present at the center of each face besides the ones that are at its corners. 3. End-centered unit cells. In such a unit cell, 1 constituent particle is present at the center of any 2 opposite faces besides the ones present at its corners. Did you know? Additionally, cubic lattice structures allow slippage to occur more easily than non-cubic lattices. This is because their symmetry provides closely packed planes in several directions. A face-centered cubic crystal structure will exhibit more ductility, deform more readily under load before breaking than a body-centered cubic structure. The BCC lattice, although cubic, is not closely packed and forms strong metals. Alpha iron and tungsten have the BCC form. The FCC lattice is both cubic and closely packed and forms more ductile materials. Gamma iron, silver, gold, and lead have FCC structures. Finally, HCP lattices are closely packed but not cubic. HCP metals like cobalt and zinc are not as ductile as the FCC metals. Summary. Let us summarize what we have learned. Solids have definite mass, volume, and shape. In amorphous solids, the arrangement of constituent particles has only short-range order, and consequently they behave like supercooled liquids. In crystalline solids, there is long-range order in the arrangement of their constituent particles. On this basis of nature of interactions between their constituent particles, they can be divided into 4 categories, namely molecular, ionic, metallic, and covalent solids. The constituent particles in crystalline solids are arranged in a regular pattern which extends throughout the crystal called crystal lattice.